You may have noticed that integrals are a lot harder to compute than derivatives. For instance, you know how to compute something like the integral of x to the 28th power dx, but you don't know how to compute something like the integral of 10x times 5x squared minus 1 all to the 28th power dx. At least not without a lot of effort. You'd have to multiply that out and turn it into some kind of polynomial and then integrate term by term, but that would take forever. So we need a new technique to deal with different kinds of integrals. And the technique that we're going to use, I'll show you right now using this integral right here. So this was the one I had before, 10x, 5x squared minus 1 to the 28th. And what I'm going to do is I'm going to try doing a substitution. So first thing I'm going to do is I'm just going to rewrite it by putting the 10x right next to the dx, just moving it around so things are a little bit easier to see. And so I'm going to say let's let u, letter u, be this thing that's right in here. So that would be 5x squared minus 1. Okay, now you might not know why I'm doing this right now, but just watch, you'll see that something amazing is going to happen here. So if that's u, then we know that du dx, the derivative of u with respect to x, would be 10x. And that's interesting. 10x is right there. In fact, if I think of the du and the dx as differentials, I can rewrite this as du equals 10x dx. And that's even better. 10x dx is that whole thing right there. And what this enables me to do is to rewrite the integral in terms of just u. So if I wanted to now, I could say this is the integral of, and this thing is u to the 28th power. Remember, u is 5x squared minus 1, so that's u to the 28th power. Great. And then I have 10x dx, that's just du. And this is an integral I know how to do, u to the 28th du. Very easy integral. That would be 1/29th u to the 29th. And then I need to have a plus c, of course, since it is a indefinite integral. And then I don't want to have a u in the answer. It'd be nice to have x in the answer, but that's okay. U is just 5x squared minus 1, so this is really the same thing as 1/29th times the quantity 5x squared minus 1 all to the 29th power plus a constant. And if you want to check this, so we can do a check here, just to make sure that this actually does work, we can check this by taking the derivative. So if I take the derivative of my answer here, which was 1/29th, 5x squared minus 1 to the 29th plus a constant, I can see that I get back the same thing. So I would do 29 out front, that would cancel with that. And so that would leave me with 5x squared minus 1 to the 28th times the derivative of what's inside by chain rule. That's 10x, and then the derivative of a constant is 0. And you can see that this is indeed what I started with. And see, there it is right there. So this technique is very useful. You can't use it all the time, but when you can use it, it's great. And it's known as the substitution rule, or some people call it a U-substitution. We have the letter U right here. You could have used any letter, but U is typically used if you look in textbooks. A lot of them will use the letter U. So let's look at this in a little bit more detail. So here's the basic idea. Here's the integral that I had before. And if you notice, we have something in here, this 5x squared minus 1 thing. And then we have the derivative of that, which was 10x. So I don't know if you just want to call this thing blah. I have a blah, and then I have a derivative of blah. So I have a dx of blah. So whatever that blah thing is, we need to have its derivative somewhere in the integral. And when that happens, then you can use this very clever rule, the substitution rule. So we want to look for something in the integral whose derivative appears elsewhere in the integral. And when we can find something like that, then we can use the substitution rule, or sometimes people call it a U-substitution. Okay, so once more consider this integral that we were talking about before. Notice that this kind of looks like composition of functions. If I have f of x as being x to the 28th power and g of x as 5x squared minus 1, then we see that inside the integral here we have f of g of x. That's 5x squared minus 1 all to the 28th power. And we also have the derivative of g prime of x. That was 10x. And so in general, we have something that looks like the integral of f of g of x times the derivative of g. And that's the general form that we want to look for when we're using the substitution rule or U-substitutions. So let's continue with this and see how this actually works. So we have the integral of f of g of x times the derivative of g, and I'm going to suppose that capital F prime is equal to f. So I can rewrite this in terms of my capital F here. And when I do that, I see that I have something that again looks like composition of functions, and it'd be nice to rewrite this maybe in terms of capital F. Well, notice that the derivative of capital F of g of x by chain rule, that's what this thing is right here, is, well, the derivative of the outside function, that would be capital F prime of g of x, times the derivative of what's inside, which would be the derivative of g prime of x. And that's what shows up in the integral. And see, we know that derivatives and integrals are inverse operations of each other, so if we know that the derivative of f of g of x is this thing, then we know the integral of that thing must be f of g of x. So I can write that there, and I'm going to tack on the constant since we have an indefinite integral here. Now, let's try and connect this to u. So let u equal g of x. That's essentially what we've been doing here. Then we know that du dx is g prime of x, or if I treat them like differentials, du is g prime of x dx. And so that tells me then that this integral that I started with, the integral of f of g of x times the derivative of g, written in terms of u, would look like the capital F prime of g of x times the derivative, and then that in terms of u would be capital F prime of u du. And that's just the integral of little f of u, because remember, capital F prime is little f. That's the substitution rule in a nutshell. So here it is, the substitution rule. So first, just to be precise here, I have to say a few things. Suppose that u equals g of x is a differentiable function whose range is an interval I. Also suppose that f is continuous on I. Now you don't need to worry too much about this kind of stuff. This is just to make sure I cover all my bases here. So now we can actually state the substitution rule, and that says that the integral of f of g of x times the derivative of g is equal to the integral of f of u du. So what we're essentially doing is we're taking something that's a nasty integral and turning it into something that's a nice, happy integral, something that you know how to do. Now you can't do this all the time, but when you can do it, it works really well for evaluating integrals. Let's look at another example. How about the integral of 6x cosine of 2x squared plus 5 dx? Now sometimes you might not know what to pick for u. Remember, we have to do a u substitution here, and it's not always obvious. For example, let's just try some things out. Let's suppose I said u was 6x. And so du dx would be 6, but since we're talking about differentials, I'm just going to go ahead and write it as du equals 6 dx. Skip that extra step there of writing du dx first. Okay, well, I don't see how this is going to help me evaluate this integral because I still have that cosine of 2x squared plus 5 there, and that's not going away, so I don't think that's going to work. How about if we let u equal the cosine? Maybe that'll work. So I have u equals the cosine of 2x squared plus 5, all right? So let's find du, the derivative of this, and so the derivative would be negative sine of 2x squared plus 5, and then by chain rule, the derivative of the inside would need to be tacked on. That would be 4x, and then I have my dx. I don't see the sign of anything in here, and you probably could tell that already. You know that the derivative of cosine is going to involve a sine, and we would need to have that sign appear somewhere in the integral, and it doesn't. That's no good. So I think there's really only one obvious choice left. How about 2x squared plus 5. Let's try that. Well, then du is going to be 4x dx. Remember, whenever you have a d something on one side, you better have a d something on the other. And this is good because I do have an x dx here. X dx shows up here. Here's the x and the dx. They're not right next to each other, but that's okay. You can move the x over there if you want. So that's the thing I want. In fact, I might want to rewrite this a little bit. Since I want x dx, I can say that x dx is du over 4. Great. Now I can write the integral all in terms of u. Remember, when you're doing the u substitution, you have to have it all in terms of u. No x's allowed. So this is going to be the integral of, so I have that 6 there. I'm just going to leave the 6. In fact, I'll move it outside. Then I have the, I'll do the cosine first here. The cosine of, and in this case, it's just the cosine of u, since u is going to be 2x squared plus 5. And then I have the x in the dx. X dx is du over 4. So let's write that. Now remember that du over 4 is just 1/4 times du. So that 1/4 is a constant. That can be pulled outside. So this would be 6 over 4 times the integral of the cosine of u du. Great. That's a very easy integral. This 6 over 4, by the way, that's 3/2. The integral of cosine is just sine. So this is sine of u, and then I have to tack on a constant, plus c. Notice when I do the integral, my integral sign and the du vanish here, so I just have this. And then I want to plug back in for u. I don't want it in terms of u, I want it in terms of x, but that's easy to do. I can do the sine of u. What was u? Oh yeah, 2x squared plus 5. So this is 2x squared plus 5 plus c. Okay, let's check it just to make sure that this does actually make sense. So for my check, I want to do the derivative of my answer here. That would be the derivative of 3/2 sine of 2x squared plus 5 plus the constant. All right, and when I do the derivative of the sine is going to be a cosine, and that 3/2 is just going to hang out front. So this is cosine of, and the inside stays the same. And then by chain rule, I do the derivative of the inside, that's 4x. And the derivative of the constant goes away, and I think you can see now that the 4 and the 2 will cancel to leave a 2 behind, and 2 times 3 is 6. So this is the same thing. I have 6 cosine 2x squared plus 5, and then I have that x left over, which looks just like this if I move the x over, and I have the same thing. So yep, it checks out. Let's look at one more example. How about the integral of x times the square root of 3 minus x squared dx? So again, we want to try and pick something for u, and it helps to kind of take a step back and think about it. What could be something that would work? Well, I could let u be just the x here. I have the x out front, but that's not going to really help me because the derivative of x is 1, and well, that's not going to help me get rid of this or make this square root look any nicer. I do see that I have an x squared here, and I know the derivative of x squared is 2x, and there's an x out front. So let's try maybe saying that u is x squared. How about that? So if I do u is x squared, then I have du is 2x dx. Well, that's still not going to help me get rid of the 3 here, and it would be nice to have just the square root of u here. So I'm going to scrap that, and I'm going to say let's try letting u be the whole thing under the square root. So we'll say u is 3 minus x squared. So then du is going to be minus 2x dx, and I like that better. That seems to work a little bit nicer. So that means that x dx, which is what shows up in the integral here, x dx is du over negative 2, or if I prefer, negative 1/2 du. Okay, so the integral now is going to be, so I have the integral of u, or the square root of the integral of u, and then I have an x dx. X dx is negative 1/2 du. And that negative 1/2, of course, can come outside the integral. It's just a constant. So I end up getting the integral of the square root of u du, and that is a very easy integral. So I have negative 1/2, and this is really u to the 1/2 power. And so when I do the integral, that's going to be u to the 3/2 power divided by 3/2 plus c. And remember that when you divide by a fraction, that's the same thing as multiplying by the reciprocal. So it's the same thing as multiplying this by 2/3, and the 2's would cancel. So I would end up getting minus 1/3 u to the 3/2, but u was 3 minus x squared. So I'm just going to put that back in to the 3/2 plus c. All right, let's check it and see if that does actually work. So for my check, I'm going to take the derivative of this. Let's see if it does work. So I have the derivative of negative 1/3 times 3 minus x squared to the 3/2 plus c. Okay, so when I do the derivative, that 3/2 is going to come out front. So I have negative 1/3 times 3/2 times 3 minus x squared, and then this will be a 1/2 now. And then the derivative of the inside would be minus 2x. And the derivative of the constant will go away. And let's see what we have. Well, the minus and the minus is going to make a plus. This 3 and that 3 will go away. And this 2 and that 2 will go away. And so I'm left with an x. And then 3 minus x squared to the 1/2 power. And I think that's what I started with, because something to the 1/2 power is the same thing as a square root. So this is the same thing. So the U-substitution, or the substitution rule, will help you to evaluate certain integrals. It's not going to work for everything, but when it does work, it makes things so much easier.